Here's video 1 for the DC motors. So for this unit, I want you to be able to discuss how torque load affects the performance of a DC motor. I want you to be able to calculate the characteristics of a DC motor at different voltages. I want you to be able to calculate the maximum load that you can place on a motor and calculate the number of motors needed to handle a specific task. So first off, what exactly is a DC motor? DC stands for direct current. When it comes to electricity, we can think of it in two different types. We've got AC, which is alternating current, and DC, which is direct current. AC is what you would have coming out of like a wall outlet. It alternates between positive 120 volts and negative 120 volts, or 110, negative 110, somewhere around there. DC is direct current, so it stays at a constant current, or a constant voltage. So for us, it's going to stay at a constant 7.2 volts. So it's a direct current. So actuators then, and that's basically what these are called. Actuators are some sort of mechanism that acts upon the environment. The most common actuators then are servos and DC motors. So a servo is an electronic or electric motor that cannot make a full rotation. So for a lot of times these are used for the steering in RC cars. There are other uses for servos, but the most commonly used ones you'll find is, if you build a radio-controlled car, you use it for the steering, maybe for the throttle as well. The DC motors then, basically it's some sort of device that's going to convert electrical energy into circular motion. So just to reiterate then, DC is for direct, and AC is for alternating. They do make AC electric motors. Those do exist. But for us, since we're using batteries, we're going to stick with DC. Okay, load. Motor loading. A load is an external torque that you place on a motor. So if you attach any kind of swinging arms or wheels, that would be a load. To visualize load, what you can think about is if you put a wheel on a motor and let it run, and then you grab a hold of the wheel, you'll hear that motor kind of get a little louder and try to work against you. When you're physically slowing down that wheel, you are putting in a greater external load, or a greater external torque onto that motor. Now, motors themselves are response units. In its purest form, a turning electric motor, or turning DC motor, has no torque. None whatsoever. The torque that a DC motor supplies is in response to the load you place on it. And again, this is really hard for younger students to grab a hold of. If there's no load on the motor, it's going to spin very fast with no torque. And this is actually true for all motors, even gas motors. So the higher the load you place on the motor, the more the motor is going to fight back with an opposing torque. This will then cause the motor to slow down its rotational speed. Now, if you continue to place higher and higher loads, or if the load continues to increase, the motor is going to slow down and eventually stop. When it stops, that's what we call stall. So when you stall a motor, that's when you've placed a load so great onto the motor that the motor stops turning. That's very dangerous for airline pilots. Current. Again, we're using direct current motors. So an electric current is a measurement of how much charges pass a point every second. So we can think about it, how many little electrons flow through the motor. That's the current. So if we have a great number of electrons flowing through the motor per second, the motor is pulling a large amount of current. If there are very few electrons passing through the motor per second, it's pulling a very low current. The unit of current is ampere, or amp for short. Now, a DC motor then draws current based on how much load is placed on the motor. As the load increases, the amount of current draw increases as well. So if I make a graph of current, and we use a capital I for current, versus the load, and load is torque, so it's measured in Newton meters, what we would see is a direct relationship between the load and the current. So as I increase the load on this motor, the current that the motor draws from the battery increases as well. So the current kind of is a changing variable. It changes. So when you just have a motor just with no load on it, it's pulling very, very few amps. But as you increase the load, the current that it gets drawn from the battery increases. Now remember, as load increases, the motor's rotational speed drops. So if I were to make a different graph of speed, measured in RPM versus load, again, I would see a direct relationship, but this time it's an inverse relationship. So as the load on the motor increases, its rotational speed decreases. There are 4 motor characteristics that you need to know: stall torque, free speed, stall current, and free current. So these are pretty easy. The stall torque is the amount of load that will stop a motor. Free speed is the maximum rotational speed of a motor with no load. The stall current, remember that as you increase load, the motor draws more current from a battery. So this is the amount of current that the motor draws when it's stalled. So if you forcibly stop a motor and it's still connected to a battery, it's still going to pull electricity from that battery, which can damage the sensitive wires inside the motor. Free current then, whenever a motor is turned on, it's drawing current. So the free current then will be the amount of current the motor draws under no load. So we can develop some graphs now. This first one is the speed versus load torque, and we've already seen this one, but we can start putting some more values on here. So at this very top here, this would be your free speed. And notice that it happens when I have zero load. Down here is where I would have the stall. And notice, again, that's where I would have zero rotational speed. Coming over to this next graph, this is a current versus load. So starting out, I have my free current, and notice again that's where I have zero load. And as the motor, as the load is getting higher and higher on the motor, let's say this point right here, where I would have my stall torque, I would have my stall current. Notice that this graph does have a y-intercept. And that y-intercept then would be the value of the free current. Alright, that concludes video 1.